So, well, great pleasure to have Akshay here representing Oxford. I think Nicholas was still representing the wider world until next week or something. So, anyway, he's going to tell us about Carrollian amplitudes from holographic correlators.
So, thanks a lot for giving me the opportunity to speak here. I'll be telling you about Carrollian amplitudes from holographic correlators, but let me spend some time telling you what these words are. Sure. So my talk is going to be centered around one basic question. In ADS-CFT, we're used to the fact that there is quantum gravity here, and there's a CFT at the boundary. ADS has a length scale. Let's call it L. This is the radius of curvature. And if you want to get flat space physics, one thing we can do is just take L to infinity. But from the dual perspective, you have a CFT, and in general, there is no length scale associated with it. And the question is, what can you do to the CFT which is dual to the ADS, to recover flat space physics? And so this is the question that I'll try to address. In particular, we want to take CFT correlators, do something to them, and reproduce. So if 3D CFT correlators, do something to them and reproduce 4D scattering amplitudes. So this is the basic question I'll try to address. So this in itself sounds interesting, but maybe you might be asking why. So there are more reasons to be interested in them. The first is that it might tell us something about flat space holography. And secondly, one reason we like ADS-CFT is that there are consistency conditions for Euclidean CFTs, which are well understood. And we could hope that if we understand this procedure of taking the flat limit, or its whatever its analog is in the dual CFT, we could try to understand some limit of this as consistency conditions on flat space amplitudes. So that is another. And thirdly, there are a lot of examples of CFTs out there, and people have computed a lot of correlation functions. And these computations have been carried out non-perturbatively. So if we understand what to do with them, even if we don't know both sides of the duality, you can start taking CFTs and start taking and start doing whatever this. So there will be a specific limit called Carrollian limit, which is the analog of the flat space limit. And so there are a lot of examples of CFTs out there, and you can just start taking Carrollian limits of these CFTs and see what you get, and check whether it corresponds to some bulk scattering. So that's examples. And of course, we have well-known examples of ADS-CFT. This is either n equals 4 super Yang-Mills, type 2B, or ABJM and M theory. We also have Chern-Simons matter theories. Of course, ABJM is a specific example, but more generally, and then these are dual to some Vassiliev higher spins. And one could imagine taking Carrollian limits of these, as well as and comparing them to flat limits on the other side, and learning something about flat space holography, or more optimistically getting top-down models. So this is the broad motivation for what I'm going to tell you about today. Let me start with the outline. So first I'll define everything, and then I'll review a few basic facts about ADS-CFT, and then tell you how we compute observables here. And then I will tell you about the flat limit from the bulk perspective, and finally from the boundary perspective. So for this talk, I will be in 3+1D bulk. So this implies a 2+1D boundary, and I will only consider scalar fields. Okay. So let me first define ADS. I'll just give you the metric of ADS in specific coordinates. These are the coordinates I will use throughout the talk. So this is ADS4. It has 4 coordinates, R, U, Z, and Z bar, and all of them are real. So R is not the standard radial coordinate. It can also take negative value. And these coordinates are called Bondi coordinates. So these are ADS Bondi coordinates. And so you can approach the boundary by taking R to infinity, plus or minus infinity, and then rescale the metric. And you can see from here what you get is the boundary of ADS4 and this is just Minkowski 3. This is just Minkowski 3 in standard Cartesian coordinates.
What happens to the S?
Okay.
So you say Z and Z bar are real. What does the bar mean then? It's not complex conjugation.
So Z bar is the, if I'm working in 3+1 dimensional, 3-1 signature in the bulk, Z and Z bar are conjugates of each other.
So you don't mean they're all real. You just mean there's a reality condition that Z bar is the complex conjugation.
Yeah. So what I wanted to say was R can take both positive and negative.
So the real part is okay.
And you could also take the flat limit here, L going to infinity, and what you get the flat limit here is smooth, and you approach Minkowski 4. These are Bondi coordinates in Minkowski, in 4-dimensional Minkowski space. And finally, you can either go to the boundary here, or you can take the flat limit here. And what you recover is the metric at Scry. So this is 0 du square plus 2 ECTC bar. So there's a null direction here. The metric is degenerate because I'm taking L to infinity. And the same thing happens if you take the boundary, if you go to the boundary here. And so one thing you can see is that if you formally, already here, if you look at this metric, you can formally identify C, 1 over C and L. And taking L to infinity is the same as taking C to 0 in whatever theory lives there. So at the level of the metric, if I rewrote this as C squared dt squared plus 2 dz dz bar, at the level of the metric, I can take a Carrollian limit and achieve the same result as the flat space limit. And what I will do with the rest of the talk is see how far we can push this. It works at the level of the metric, and what we'll check is that it also works at the level of correlators, and you can.
It's jumping ahead too far, but in your explicit sort of top-down examples, when I did that, did the internal space also decompacted? So I'd end up in 10 dimensions rather than 11 dimensions rather than.
Yes, so that would be something we would have to worry about if we are looking at these.
And I might not see that if I just looked at 4-point correlation functions, but I certainly would see that beyond 4-point correlation functions, and I might see it at loop level as well.
Yes, it's not obvious that I wouldn't see it at 4 points.
I was thinking that if I've only got 4 points, I can maybe combine them and it's allowing you. That's the wrong one.
That's a tree. Oh.
That's a tree.
Yeah.
So, I mean, are your results about correlation functions going to be sensitive to things like that, or?
So everything I look at here are just going to be tree-level and scalars.
I wouldn't expect to see those problems.
At here, I wouldn't expect to see any problems, but we haven't gotten to analyzing those yet. We expect there to be more subtleties of that. So the slogan that we use is that flat limit in the bulk is the same as Carrollian at the boundary. And we'll see that this works at the level of correlators as well. So what do we want to compute? So first of all, we want to take the flat limit of observables in ADS. And in a local quantum field theory, we could just compute local correlation functions, but with dynamical gravity, we can only compute boundary correlators. I'll define them more precisely in a moment. So here, there are two questions you can ask. Once you have the boundary correlator and you compute it perturbatively in ADS, and you take the flat limit, what do you get? So flat limit. What do you get? And the second question is, suppose you have the dual CFT description of it, and you express it as a CFT correlator. How do you reproduce? Whatever you get here? So let me first tell you what boundary correlators are, and then what you get when you take the flat limit. So asymptotically, the fields become free, and I can solve box plus m squared phi equal to 0. And the solutions of this near r goes to infinity look like this. Where delta 3 minus delta. And what we usually do is we impose some boundary conditions and we get rid of this. So these are the, and I can define boundary correlators, boundary operators this way. So it's picking out a specific large R behavior. And there's also an extra label epsilon, which tells you whether I'm taking the large R to be plus infinity or minus infinity. And the correlators we compute would be correlators of these operators. So these would be the objects of interest. So you can compute this perturbatively from the point of view of ADS. Of course, the whole point of the ADS CFT correspondence is that there is a dual CFT in which you can compute them in a different way. Okay. So let me briefly outline how these are computed. And along the way, I'll describe the flat limit. So these are computed. So
are all of the epsilons the same, or are they all different? And if it's possibly different, do you get some sort of factorization happening where you have operators sort of infinitely separated from one another?
So the epsilons are all different, but sorry, what factorization?
Oh, I was just curious if you're like taking the insertion points to infinity in R, then I might imagine the ones that are negative R and positive R are like infinitely far separated, and so the correlation might factor.
But in ADS, the boundary is connected. So even though I'm taking R to plus and minus infinity, there are actually different points on a connected boundary. So they don't necessarily factor. But what I will show is that once you take the flat limit, the ones with epsilon equal to +1 become out states, and the ones with epsilon equal to -1 become in states. In the flat limit, they are kind of on scri plus, scri minus. If you're used to thinking of ADS as a cylinder, the boundary coordinates cover multiple Poincare patches of the cylinder. So R equals plus infinity is on one Poincare patch, and R equals minus infinity is on the other Poincare patch. So the green line is a line of constant U, Z, and Z bar, but it varies in R. So I'll consider a theory in the bulk which has two kinds of interactions. There's a cube and a quartic. This is just for illustrations, and so we want to compute boundary correlators in this theory in ADS. And the way they're usually done is via Witten diagrams. So these are just analogous to Feynman diagrams with slight modifications. So So the little xi are three-dimensional, and so they just have u, z, z bar. But the big xi are coordinates in the bulk, so they have 4 coordinates. And there are two kinds of Feynman rules that go into here. The red lines are bulk propagators. So they connect 2 points in the bulk. So these are solutions to this. Where m squared is m. And with a specific boundary condition which kills off one of the modes. And I can write down the solution. There's some normalization, and then there's a coordinate dependent factor and a hypergeometric function. So I am in Lorentzian ADS, so these need an I epsilon prescription in order to be well defined. So this is the Feynman I epsilon. And C12 is the geodesic distance between the points x1 and x2. And I can write this as minus 1 over x squared. So this is the distance in flat space and the correction coming from ADS. This is not an approximation, this is the exact result. And what you can see is that this goes over, as you take the flat limit, the distance obviously goes over to the flat space distance. But what you can also show is that if you take the bulk propagator and take L to infinity, it just reduces to the Feynman propagator. And an important point here is that it is this limit, the result of this limit is independent of the value of delta. So I can take any value of delta and I get the same limit. The only caveat is that delta should not be parametrically large, that delta shouldn't scale with L. As long as that is satisfied, I get the Feynman propagator. Okay, the things in green. So everything is becoming mass space. The things in green are the bulk boundary propagators. And these can be defined in terms of the bulk propagators. They're defined.
And C2 is some function delta?
Yeah, it's a normalization factor. It involves gamma functions.
Oh.
You get the massive Feynman. So here, you take the bulk propagator and push one leg to the boundary, and you get the bulk boundary propagator. And I can again write it down in Bondi coordinates. And what you can show is that once you take the flat limit, again, I'll go into infinity, you get something. Looks like this. So another feature here is that depending on whether I take R to plus or minus infinity, there's a different sign to the I epsilon regulator. So there's a bulk boundary propagator associated to incoming and outgoing, and that they differ by the I epsilon prescription. And so on taking the flat limit, I get that, but it's more illuminating to write this as a kind of a Fourier-Mellin transform. So Q1 is just the point is just that if you take the bulk boundary propagator and take the flat limit, what you get is the Fourier transform of a plane wave, or a Fourier-Mellin transform of a plane wave. So if you want to take the flat limit of a correlator like this, now that we understand the flat limit of all of its constituents, it's easy to write down. So let me...
You have to integrate the vertices.
Yes.
Over what? Exactly?
So here you're integrating over ADS, and once you take
Would
the...
it be over all of ADS or over that shaded region that you've got? I mean, sorry, yeah. You should integrate over all of ADS.
You should integrate over all of ADS. And once you take the flat limit, that just reduces to an integral over flat space.
What happens to the bits of ADS that are not entangled in the shaded region? Is it into the boundary coordinates?
So this is all of ADS can be covered by two Poincare patches. The body coordinates cover all of ADS. So, and once you take the flat limit, it's smooth, and the measure just reduces to a measure over Minkowski.
So I know when the right time to ask this question is, but on the right board there, you got two solutions because it was a second order equation evolving in the spatial direction, and so you could kill half of them. But when I take this flat limit, my boundary is in the null direction now, right?
Yes.
And the Laplacian becomes first order when I'm evolving it in a null direction. So shouldn't I worry that I only have half as many solutions somehow, and that this prescription of separating out the delta from the 3 minus delta stuff is going to break down?
But at least from the computations we've done, it doesn't seem like anything breaks down.
It seems like conceptually something should. So it's the question is where that shows up, because what you're doing in ADS-CFT, you're basically identifying one of those solutions with the source and one of them with the operators of the dual field theory. But if I have a null surface, then my commutator becomes all on the same surface, and it seems like it's going to be require something more artificial to do that decomposition.
So maybe it's that R goes to minus infinity and R goes to minus plus infinity. That got something to say. I'm sure.
I think maybe you double the solutions again because you go in both directions, and somehow it compensates.
I'm not sure. Sorry, it's just a random guess. I don't know. Sorry.
So once you take the flat limit,
Right.
the precise value of delta stops mattering to some extent. So in this we chose a particular value of delta, but in principle we could have tried computing correlators with the other value of delta, and we could see what you get.
But that's it. You just mean like if I look at these the equations, I don't see delta anywhere in it. Is that the idea?
Yeah, you don't see it anywhere in the bulk propagator, but you do see it in the bulk boundary. But
that's where you'd worry about boundary dimensions.
right, but one thing to note here is that shifting delta to delta plus 1 is the same as taking a u derivative because of this factor. So the information in the rest of in delta is kind of redundant because it just encodes derivatives in u. So the precise value of delta here doesn't matter anymore.
If I don't care about how things are localized to the u direction, either.
But the correlators we get would be translation invariant in the u.
Okay.
At least the translation invariant.
And that's why you're saying you don't think of that. Well, I should let you keep going.
Sorry. Okay. Now, let me just consider a diagram like this. And if I were to write down the expression for this written diagram in ATS, I would integrate over both points x1 and x2. I would integrate them over ATS. I have bulk boundary propagators. And then I have the bulk propagator. And once I take the flat limit, I'm just left with an integral over Minkowski spacetime. And let me use the fact that the flat limits can be written as Fourier transforms to do this. And there are two factors of coupling from the 3-point and the 4-point vertex. And there are the main wave factors. And the point is just that this whole object you can recognize as as the Feynman rules for a momentum space amplitude. With the momenta pi identified with omega I qi. And this is just some sort of a Fourier-Mellin transform. And the upshot of this is that if you have a Witten diagram in position space and you take the flat limit, what you land on is the Fourier transform of Fourier-Mellin transform of the momentum space amplitude. And so these objects are called Carrollian amplitudes. So I denote them by this.
So I can talk to that, but green on green is not perfect for those at the back.
Okay. I can stop.
Sorry, no, don't. I think.
No, I'm not going to change everything. I was just going to.
Oh, okay. Yes, you have to rewrite the whole talk from the beginning.
So these objects are called Carrollian amplitudes. So these Carrollian amplitudes are functions of positions at scri. And and they're Fourier transforms of the momentum space scattering amplitudes. Because this is a celestial day, I should add that these Carrollian amplitudes. So these Carrollian amplitudes can be thought of as amplitudes you get when you, instead of scattering plane waves, you scatter these position eigenstates at the boundary. So in that way, you can just view it as a change of basis from momentum states space to position space. And the celestial amplitudes are a change of basis from momentum space to boost eigenstates, and so there is a relation which relates Carrollian amplitudes to to celestial amplitudes, and if I call these and the relation is given by just integrating over u. Of the Carrollian amplitude.
What happened to the omega to the delta minus 1 factor that you got from the flat space limit of the
so because so like I said, a shift in delta by an integer doesn't matter. So in writing this, I'll just set delta to 1. But in general, we will need to consider all descendants. These are u derivatives of the amplitude, du1 to dun of c. And by taking such derivatives, you can insert arbitrary integer powers of omega there. So just for simplicity, I've got rid of that fact. And in principle, these are much easier to compute than objects with omega.
Do you know what delta should be set to a priori?
So there are specific values of delta which are important from a bulk perspective. So for example, if you're computing gravitational amplitudes, delta equals 1 would correspond to the shear, which is a specific large R component of the metric. And delta equals 2 would correspond to the news. There are specific values of delta which have physical meaning.
So if you start off with a CFT, where you know what delta is for a particular operator, and then you take the flat space limit, presumably delta should be preserved.
So if you start from a 3D CFT and you take the flat space or the Carrollian limit, the delta remains. And so what you land on are not these, but you land on these things with an arbitrary value of delta. But they can be, so one different values of delta in the CFT will give you this Carrollian amplitude and also all of its descendants. And I'll show that explicitly in a bit.
Going back to your previous point, naturally suspicious, but is there a reason you're illustrating it with 5 points rather than 3 points?
Oh, I just wanted to combine both vertices.
In particular, I shouldn't be worried about any sort of order of limits of doing the ADS integral and then taking L goes to infinity, or first taking L goes to infinity and then taking integral. That's all fine.
That's all fine, but also the second part, the part I'll get to now is about doing the ADS integral first and then taking L to infinity. And I will show you that you can actually reproduce this.
About 3 points, for example.
At any number of points. So these Carrollian amplitudes have been computed. And for the specific case of scalars, I've written them out here. I've written them out for specific configurations. Just for convenience. There are a few features that I would like to point out. These are weird functions, they're distributional. And these distributions arise from the fact that 3-point amplitudes and 3-point amplitudes are, you cannot solve momentum conservation and on-shell condition at 3 points, and those are that is encoded by the delta functions. And the different, and kinematics imposes constraints on the Z1, 2. The 4-point function is also distributional, and there's a delta function here, which is a reflection of the fact that momentum conservation at 4 points forces you to be on a plane. Well, and apart from that, there are functions of the u's and the z's and z bars, and and the goal now is to start from CFT 3-point functions and reproduce them. So, okay, I've also written down CFT 3-point functions, which everybody knows. So these are 3-point functions for scalars with arbitrary values of delta. And so the goal is to take this, which looks nice, and turn it into this. Okay. And the key to doing that would be to take the Carrollian limit and to take it carefully. Okay. Any questions?
So to what extent are these Carrollian amplitudes just what you'd exactly have expected from a 5 plus 5 to the 4th amplitude in space-time?
Sorry, could you say that again?
So you've taken this limit, you've done some correlators, and you've taken some limit, and you might have guessed that the answer that you would get would be precisely what you've got had you started with a phi cube plus 5 to the 4th amplitude in flat space. Is that true, or is there something
literally
subtle?
true. It's true on the nose.
That's true on the nose.
So
Okay.
when you take the flat limit, you get the amplitudes that we computed.
I see. Yeah.
Right? You get the integral representation of the amplitudes we computed.
Mm-hmm.
But if you were to do the ADS integrals, then you would end up with something that looks like, at 3 points, for example, you would end up with something that looks like a conformal field theory 3-point function. And then it's not obvious how you would recover this beast from this. But that's the next 14 minutes. Okay, so let's start at 3 points.
This 3-point function is a Lorentzian correlator.
Well, this
Before
technically
you
is
take
a
the-
Euclidean CFT, but I can analytically continue it to do signature.
No, you're taking a limit of the 3-point function from 3D CFT.
3D CFT.
And that's in the ADS case, we're starting with a Lorentzian CFT.
I'm starting with, okay, because 3D. I'm starting with a 2-2 signature ADS bulk, because that's where this amplitude is.
Okay, regardless, I was going to ask, you probably need some I epsilon prescriptions to make sense of the...
Yes. Yes, that'll be there. Here I've written down in Euclidean, so there's no I epsilons.
Oh, that was Euclidean, okay.
So we can start trying to take the Carrollian limit of this, and the naive limit is a spectacular failure because you just get something which has only the two-dimensional coordinates. And it has no time dependence. But this is known to be a kind of Carrollian CFT, and this is called a magnetic. This is the correlation function you would expect in a magnetic Carrollian CFT. It is characterized by the fact that there is no time dependence. And the idea is that this is secretly three-dimensional, but it has no time dependence. But this is clearly not what we want. It looks nothing like that. So we have to take the limit more carefully. So the idea is if I take the limit c going to 0, this result is true on most configurations, but precisely on the configuration where x12 squared happens to be 0, I get something which looks very different. I get something which looks like 1 over c squared equal to squared to the delta 1, 2. And so I have to pay special attention to these special configurations on which there is an enhanced Carrollian, enhanced c going to 0 behavior. And this is kind of reminiscent of this formula that everybody knows. And the idea here is that in general the limit is 0 unless x itself is 0, and in which case you get a delta function. And there is a bit more to it because this has to integrate, this has to have a finite integral between minus infinity and infinity. So I will rewrite this in a slightly looser way and just say so we want to expand functions like this, taking care to keep the distributional pieces. And if we do that carefully, the idea is we will recover the 3-point amplitudes written here. I won't demonstrate everything explicitly, but I'll just tell you some of the key features, in particular how you would recover the theta functions and the delta functions. The delta functions might be obvious because by now because of this formula, but so what we look for is some limit like this. And I have to determine what the power alpha is, and I have to determine the function g. So this is given by so if I ensure that this integral is finite and non-zero, that picks out a specific value of alpha, and it also tells me what the function g is. So with the rest of the task of reproducing the amplitude is essentially evaluating this integral.
You want to integrate it to parts.
Yes.
Sorry, I'm a little confused. So the formula that you write down for the delta function here actually allows you to recover the Euclidean version of those correlators, right? Like these Carrollian amplitudes are written in bulk 2-2 signature, or if you want to like celestial sphere that is Lorentzian.
Yes.
So you promote the Z and Z bar to independent variables.
Yes.
The formula that you wrote here, like you can prove it using the Fourier transform, it automatically is going to give you like, it's not going to give you independent delta function in Z bar.
Yes.
It's going to give you a delta, it's going to give you a delta 2
for each of the factors.
Right, a delta Z times delta Z bar.
Yes.
Yeah. And in particular, and also the prefactor that you have here that's very particular to these Carrollian amplitudes, right? That has this linear combination of UIs and ZIJs.
Yes. So
that also, sorry, I'm confused about how you get that structure from like this thing that you said about the delta.
So this formula was just meant to be schematic, just to.
It is a delta D in D dimensions. Sorry.
This formula was supposed to be schematic, just to make the limit plausible, but it's not exactly this that I will be using. So I'm using a variant of this where I look for a limit which has these two delta functions and determine the coefficient here. So this is, I'm assuming I'm working in two signature in the bulk, and I'm looking for a limit like this, and the question is just whether this exists and I can find a G and an alpha which satisfies this. There could be other terms here with different numbers of delta function, and that's not something we've explored.
I mean, I'm just wondering, is it obvious that there's going to be contributions like this? Because of course, when you do the integral, you're going to get some number that you can match to the function.
It's not a priori obvious that it should be finite. You could get something infinite. The integral could just not converge anywhere. And also, this number G should match this. But that seems not trivial.
Okay, sorry, you should ask.
Okay. So all we need to do is evaluate this integral. I've already reproduced the delta functions by assumption. If this limit exists, then the delta functions are reproduced. So the next thing to show you is that these theta functions can be reproduced. And to do that, again, I'll sketch it out, but I won't show you all the details. We can look at the Z1 bar integral and think of it as a contour integral in the Z1 bar plane. And this has two branch points because of the two denominators that can vanish. And and there are branch cuts emanating from these, and they're displaced because of the I epsilon prescriptions.
I'm not sure that thing is going to zero limit doesn't immediately become distribution. Or is he going to take a different limit, or you just still talking about that?
So,
the C going to zero limit becomes 1 over product of x1 to some power x2. That's not distribution. So yeah, if that was 0 plus in some obvious way.
Right, you can say that again.
In the C going to zero limit, if the 3-point function was 0,
yes,
and then you could argue that maybe it's distribution.
So that's why I wrote this. What you'll see is that there is a specific power of C that these come with. So if you take the limit carefully, you will get something like delta z bar 1, 2.
right? So there's some other power of C somewhere.
There's this power of C. And then you have to multiply the whole thing, and this, you have to rescale the fields by appropriate powers of C. And on the ADS side, it's like rescaling by some power of the ADS length scale.
Some positive power of C numerator so that it becomes 0. Now you
But the non-trivial thing is that this scaling is set once and for all for an operator of a given dimension, and that scaling reproduces 3, 4, and higher point amplitudes. So if I'm not choosing a different scaling for every amplitude and reproducing it.
Sorry, can I just check? So the thing that on the top right is that plus the magnetic contribution. Distribution plus the magnetic contribution.
This one?
On the top right. The equality is either equal to that plus magnetic contribution, or it's equal to that plus a big O of something smaller, a smaller power of C.
It's equal to that as long as you choose the power of C appropriately.
I mean top right. So the correlator is not literally equal to that, but it's equal to that plus the magnetic contribution.
Oh yeah, there would be other.
Because I think that was Atul's question.
There would be other terms with different numbers of delta functions and different powers of C. Okay. So the idea is to look at this in look at the contour integral in the Z1 bar plane, and it has two singularities, and the location of these singularities depend on the signs of Z12 and Z13. Now generically there are two situations where both the branch points are on one side, or the branch points are on opposite sides. And in this case, as long as there's no polar infinity, you can close the contour either way and get 0. So this is the situation. So you see that the integral is non-zero only if there is a specific relation between the signs of Z12 and Z13. And so this reproduces one of the theta functions. And a similar logic applies to the other integral, and you can reproduce the second theta function that way. And once you actually evaluate the integral, you end up with exactly this, including the prefactor. And the point is, it was finite, and there's a specific value of alpha. There's only one value of alpha for which it works. And this alpha depends on the weights delta 1, delta 2, and delta 3. And indeed, you can, at the level of the operator, you can introduce a rescaling at the level of the operator, and once you introduce this works for all correlation functions in the theory, and it gives you finite Carrollian limits which reproduce the Carrollian amplitudes. Okay. In the last minus something, I just want to tell you about.
I have to be generous to yeah. Go ahead.
Okay. The 4-point function is more complicated. It involves dialogues and logs, and the idea is to start from here and reproduce this. Once again, if you just blindly take C going to 0, you get something which is time independent, but that's not what we want. But we already learned the lesson that we are supposed to look at specific kinematic configurations and singular points of the amplitude. So Z and Z bar are related to the 4D cross ratios here. And what you can do is you can evaluate this as C goes to 0. And what you will see is that this is and what you'll see is that you can Taylor expand this in Mathematica and you get something like this. And so on arbitrary configurations where Z minus Z bar is not 0, if you now take C to 0, you will just end up with a simple pole which looks like 1 over Z minus Z bar, where Z is the 2D cross ratio. But that's not what you want. What we want is a delta function in Z minus Z bar. But the same logic works here. If I look specifically at the kinematic configuration where Z equal to Z bar, Z minus Z bar squared now behaves like 2C squared F. And 1 over Z minus Z bar has an enhanced behavior in this limit. So the idea is just on generic insertions of the operators at the boundary, you get Carrollian limits which give you magnetic theories which are time independent. But at specific configurations of the external operators, you get something which looks like scattering amplitudes in higher dimensions. So we want two things. We want a singularity as Z goes to Z bar. We want the correlation function itself to be singular. And we want to work on the specific configuration where the 2D, I'm just going to write subscripts to emphasize that they're different dimensions, but we want to work on the specific configuration where these two are, when the Z 2D is Z bar 2D. But if you look at the 4-point function here, the numerator has a 0 as Z goes to Z bar. But that's okay because this is an Euclidean. This is a Euclidean 4-point function, and what you need to do is analytically continue this Euclidean 4-point function to a Lorentzian one, and a specific Lorentzian configuration at that. So this is achieved by Wick rotation. You can just Wick rotate the time coordinate, but this is non-trivial because this function has branch points at 0, 1, and infinity, and you need to account for how you approach these branch points, and all of the polylogs pick up appropriate monodromies. And the image that you can have is, so this is the complex T plane, and this is the Euclidean slice, and you want to move, and these are the light cones, and there's a branch cut whenever you cross one of the light cones, and you want to move these into a configuration where two of the points, let's say 3 and 4, are in the future of 1 and 2. And once you do that, you get, and I'm doing that because the amplitude I want to reproduce has 2 incoming and 2 outgoing. So once you do this Wick rotation and account for all the monodromies, you will find that this actually picks up an extra piece which is singular. And you can now make a similar ansatz to the 3-point case and write this is some R and determine the function R just like I did in the previous case, and you'll find that it turns out to be exactly equal to the 4-point amplitude. Okay, I think I'll end here.
So in the interest of the break, maybe just one question. I'm going to say one behind me, sorry.
Is that you?
So,
to ask something about the 3-point case. Do you have that integral maybe on the board behind this one? The integral that gives you that fairly GFC function. Oh, you don't. Maybe you wrote it wrong.
Yeah. Okay.
That one, yeah. That generates a gamma of beta, where beta being delta 1 plus delta 2 plus delta 3 minus 3. I don't remember. And in the celestial amplitude, you're supposed to have a delta of beta. Do you have any version of that delta of beta here that might pose you a problem, or you just don't have it?
Oh, you mean delta function? No, this doesn't generate any delta function.
No, this generates a gamma of beta.
Yeah, that's here.
Oh,
It generates this one. Maybe it's not
okay, and that's not a. Oh, in this Carrollian, so you don't have a delta of beta, so that's not a problem for you.
Yeah, and in general, these deltas you could set it to be anything you want.
Oh, I see. Okay.
Except there are certain limits, certain values of delta when it's divergent, but that corresponds to UV IR divergences of the position space amplitude.
Okay, so let's find.
Quick one.
Oh, okay.
So if I look at a 2-point function,
Uh-huh.
and I'm not in a special configuration, don't you still get some non-zero answer? Like just 1 over Z1, Z2 mod squared?
You just get 1 over Z1 minus Z2 squared, yes.
But 2-point amplitude should be 0. Or at least it should be purely a delta function.
So the Carrollian 2-point amplitude is just the inner product. So the Carrollian 2-point function has a delta of Z12. So again, I need to be on the special configuration where you're at the same point on the celestial scale.
So these other branches of the Carrollian thing, by hand I have to throw them away.
No, you don't have to throw them away by hand. It says there's a specific.
But it's maybe your alpha again.
There's a specific rescaling of the operator that you can do. So the idea is that there is this operator in EDS where it's related to the Carrollian amplitude by a specific rescaling which involves powers of C. And once you fix that rescaling for the operator, everything else follows. You can actually the nice thing would be to start at the 2-point function, ensure that that has a finite Carrollian limit and the electric limit that you want. And once you do that at the 2-point function, you don't have to do any of that here. It just works.
It's probably a minus 2-point function for 2 negative STP ones.
Is that doing scales?
It's only doing scales.
Okay, let's thank Akshay again.